Hey everyone, welcome back to Chem Story. Today, we're diving into structural isomers of alkanes, what they are, why they form, and why the number of possible isomers skyrockets as the carbon chain gets longer. Have you ever looked at two alkanes with the same molecular formula and thought, how can they be different? Well, that's exactly what we're going to explore today. Let's get into it. Once an alkane has 4 or more carbon atoms, things start to get interesting. That's because the carbon atoms can connect in different ways, and those different arrangements give us what we call structural isomers. These isomers all share the same molecular formula, but their atoms are arranged differently. And that difference in structure can lead to changes in both physical and chemical properties. Some of these isomers even have common or trivial names, especially when we're dealing with smaller alkanes. So why does carbon make so many isomers? It all comes down to its unique ability to form strong, stable single bonds, not just with other elements, but with itself too. That's what allows for branching and all sorts of different ways to build a molecule. Let's take a look at some alkanes, starting from methane and going up to octane. Methane, ethane, and propane each have only one possible structure, so they don't have any isomers. But once we get to butane, things start to change. Now we see 2 structural isomers. Pentane has 3, and hexane has 5, and from there, the number just keeps growing. So what happens when the carbon chain gets even longer? Let's take a closer look. Starting from nonane and going up through pentadecane and even icosane, the number of structural isomers grows at an incredible rate. For example, decane, C10H22, has 75 isomers. Dodecane, C12H26, has 355, and icosane, C20H42, that one has a staggering 366,319 different structures. Every time you add just one more carbon, the number of possible branching patterns increases dramatically, giving rise to a huge variety of unique molecular structures. Now, let's take a look at some specific examples of structural isomers in small alkanes and see how their structures are different. Take butane, C4H10, for instance. It has 2 distinct forms. The first is N-butane, which has a straight chain structure. All 4 carbon atoms are connected in a row. The second is 2-methylpropane, also known as isobutane. This one's branched. 3 carbon atoms form the main chain, and 1 carbon branches off the center, giving it a more compact shape. When we move on to pentane, C5H12, we start to see even more variety. There are 3 possible isomers. First, there's N-pentane. It's a straight chain molecule where all 5 carbon atoms are lined up in a row. Next is isopentane, also called 2-methylbutane. In this one, a methyl group, that's a CH3, is attached to the second carbon of a 4-carbon chain, giving it a single branch. And then we have neopentane, or 2,2-dimethylpropane. This one is even more compact. It has a central carbon bonded to 4 other carbon atoms, forming a highly branched, almost spherical structure. When we move up to hexane, C6H14, the number of possible structures jumps to 5. And if you take a closer look at these isomers, you'll see how N-hexane can be rearranged in different ways to create all of them. Try drawing them out yourself. It's one of the best ways to really see how these transformations happen. Once you go beyond hexane, the number of structural isomers starts growing super fast. And these differences aren't just on paper. They actually affect physical properties, like boiling points and melting points. That means each isomer can have different practical uses, whether it's as a fuel, a solvent, or an ingredient in industrial chemicals. If this lesson helped you out, make sure to like the video, subscribe to the channel, and turn on notifications so you don't miss what's coming next. Thanks for watching, and I'll see you next time.